Hello, my name is Mehdi Bennis. I'm a professor at the Center for Wireless Communication at the University of Oulu in Finland. I'm here today to present to you a number of solutions from a communication perspective to post-earthquake management. First of all, I'd like to reiterate my condolences to all the victims of the earthquake, for all the people who have passed away, rahimahullah, but also all those injured. So the outline will be as follows. First, I'll start with UAVs, in fact, as a very viable solution in post-earthquake management. Then I'll talk to you about LEO satellites. And then I talk to you also about some RF sensing technologies, which are very useful in earthquakes and other type of disasters. So yeah, so UAVs are must-have. This is especially the case in the absence or damage of infrastructure, so base stations or some other gateways or other servers in the area of the aftermath of the earthquake. In fact, the reason for that is they are essentially critical in collecting, sensing relevant information and putting those information together for very fast deployment of emergency services, but also to optimize the dispatching of these various teams that need to be sent to a given location. Okay. Now there are a number of desiderata, so typically depends on the scenario. So you may have, for example, the case where you have, for example, a human being here as an operator or a controller, or it could be even a very remote base station which wants to dispatch a drone to the destination or to the target essentially. Here, so you need to ensure reliable communication, right? This is where communication comes into the picture, right? Again, from a base station to a user, where the user here is a drone, okay? In addition to that, in fact, relying only on one drone will not be enough, okay? Even though they may be equipped with cameras, LiDARs, because their lifetime is very limited, ranging from 10 minutes to 20 minutes, and so on, depending on the payload, obviously. But you need a swarm drones. I mean, here the message is very clear. We need a swarm drones. So how do you manage these swarm drones? How can you make them fly in harsh environments, under wind dynamics, non-line of sight, so beyond the visual operator's sight, and of course avoid collisions, right? And again, there are two types of perhaps of works here. We can think of the first one is remote control over wireless. So this is more of a kind of automated type of path planning, if you want, but also the autonomous case where you completely have fully autonomous drones, trying to reach a destination. Okay. So this second example, I'm going to walk you through some works we did in the past in my group. This is essentially the setting where you have, again, the same as before. You have a base station, but this again could be really a remote controller, right? A human, which is trying to send a drone, right, to the destination. So here, of course, the wireless part is very important. So the link between the base station and the user. So here you have different solutions. You may, in fact, try to remotely control the drone, but here you may run into issues of line of sight. The link may be noisy, interfered, right? So maybe what you want to do is to train this drone to fly on its own autonomously after some distance, right? So you can train it first, where the drone is reporting its state, right? Location, velocity, and then you can maybe try to learn a model which allows the drone then to fly autonomously. So that's essentially what we did, right? So, I mean, mathematically, this is a online path planning, right? And their travel time and motion energy, right? So energy here is very important, obviously, the battery of the drone. And again, as I told you, you can, you can either, train the drone to fly on its own, right? So you communicate the states, train a model, and try to share the model, which may be obviously large, so this isn't a good idea. Or you can, try to optimize the distance after which the drone flies completely autonomously, right? And that's what we did. In fact, I'm not gonna go through the mathematics here. This is not the purpose of this talk, but the solution is maybe more interesting here. This is your Lyapunov stability of this control problem. This is a distance. So you can see, for example, here there are three curves. The greenish here curve, essentially, this is the action uplink. So here, this means the base station is continuously transmitting to the drone. So of course it works after some distance, then it flattens out, meaning it loses packets. You may also try to now transmit the model, right, after training, obviously, right? This again can improve the performance, but it saturates obviously here the best solution is the hybrid case, right, where you switch from the action to the model-based solution. I mean, this is a very basic idea, but of course can work, in fact, right? Now, perhaps the more interesting case is in the swarm setting. So this is autonomous setting. So again, back to the same scenario here, but now I have completely autonomous drones. We have a large number of drones here, which are trying to go to the destination under wind perturbation, avoiding collision. They want to obviously optimize their path, because now they want to go perhaps directly towards the destination, but then you have also the collision and then the energy constraint. In terms of wireless here, you can have a multi-connectivity setting where the drone may be equipped with 4G, 5G, Wi-Fi, meshed, right? I mean, there are various solutions which can be explored, right? But for us, again, this was again a theoretical work, so we formulated again this control theoretic problem, where again now you have the drone minimizing its cost function. This is a state evolution of the drone. This is your drone in motion here, or just to reflect the wind dynamics. And then what was our focus here was in the case of a very large number of drones. This can be studied actually through the lens of mean field game theory, where, for those who don't know, I mean, this is when you really scale up the system, which allows you to decouple essentially the flock of drones, because to solve this control problem in the large scale setting is extremely difficult. But when you go to this large scaling setting, it allows you to in fact to decouple, right? So what you would have here, you would have what we call the Hamiltonian-Jacobi Bellman equation, which is essentially the optimal control equation for a given drone, and then this the Fokker-Planck-Kolmogorov equation here, the partial differential equation, which gives you the probability density of this flock of birds. So think of them as birds, right? So you're trying to find the velocity here, right? And by solving these equations, which are two coupled PDEs, you find the optimal control and also the velocity of the swarm of drones, right? And that's essentially what we did. Let me just go to the results. I mean, here this is assuming 25 drones. So a number of baseline. This is a first baseline where there is no. So essentially, every drone solves this partial differential equation. Just the first one, meaning the HGB1. And here, basically, the drones exchange their state at every time t. And as you can see here, this is 30 seconds, 60, 80, and 200, 90, and 200. You can see that there's a lot of collisions effect here, which are these red stars here, right? Now, if they decide to communicate their state only after 100 time slots, okay, you still have, I mean, you can see a lot of collisions here. So the best solution, in fact, is, I mean, using our proposed approach, where you see there is no collision, but there's a trade-off here in the sense that you can see here, there's a wider turn that the drones have to take to reach the destination. I mean, this is perhaps a toy example, but I think it could be relevant here in the case of a fully autonomous setting of sending drones, not only in the battleground, obviously, but now this is really the background here is the earthquake epicenter and so on, right? Okay. Now let's move on now to, in fact, integrating now another technology. So the LEOs have been very I mean, interesting recently, perhaps thanks to Elon Musk, where now we have these LEOs which are flying at a lower altitude compared to GEOs, right? So these are low Earth orbits, and they are here to, in fact, help drones charge, but also to help them forward packets, let's say, from a given sender to a receiver, where you have no infrastructure whatsoever. So this gives rise to a very interesting problem. So first, obviously, the integration, but how do you forward packets between this highly time varying network of drones and LEOs flying over their pretty determined orbits, right? So you have a very interesting optimization problem to solve. And from a wireless communication perspective, here you have the RF link, which links these drones and these LEOs, but you also have this free space optic link, which is very good typically for backhaul, to essentially help you achieve high rate transmission between the various devices in the air, obviously. Okay, so that's what we did again. I mean, here's just some result to show you, in fact, that it really works. This is the system end-to-end system throughput for a given network composed of many UAVs and many LEOs. So I mean, the hybrid setting here, where you can combine, in fact, the RF link and the FSO, to communicate completely from any part of the Earth to any other part, right, reliably is actually possible. Again, bear in mind this is just in the 2-orbit case and 2 UAV case, so obviously we need to scale that up. What's interesting, in fact, is if you check the news recently, there is this Moroccan guy, Ali on Twitter, who actually managed to, I don't know if he hacked, but doesn't matter. What he managed to do is to bring those satellites here. You can see one here. This is a Starlink satellite of Elon Musk. He brought it here and managed essentially on the fly provide an ad hoc network, which now is serving to relay information between teams, rescue teams, to relay back to the server, to the authorities, right? But not only that, I think he uses it with this EcoFlow charger, which allows to charge mobile phone, charge many devices. So this was a very smart idea, and of course you could think about extending this further, right? Instead of having one satellite, right, you could have a multitude of satellites, and this would really help provide extremely fast connectivity to all the teams, and obviously this translates in saving lives. So this is essentially what I wanted to share with regard to this satellites, right? Yeah. Now let me move on to the other technology, wireless sensing, which is a very interesting one also here, which marries many technology. You have obviously the AI, but also the RF. You have multimodal sensing and fusion. So here, this is a setting, for example, where you have, again, this is a disaster area. You have the victim here. Then you have this kind of Boston Dynamics kind of robots. You have drones. And then what you have here, this is, I hope you can see, this is a kind of a van of the AR team. And you have now the use of virtual reality glasses, which are connected to what the robot sees, in fact, in real time, right? Then you obviously have the control command, but the point being here essentially that you again deploy on the fly this network of mesh drone robots and so on in order to maintain connectivity between all these devices. So for example, if a given robot runs out of, is out of coverage, essentially it will request another robot to come and kind of serve as a relay in a completely autonomous way. Now you may have, this is the robot, which is actually equipped with a millimeter wave based sensor, right? So it's kind of going to the vitals, to get the vitals of the victim, identify whether it's still alive, not alive, and then trigger really the location basically for further intervention, right? So this is, I think, a very interesting use case. But just here to summarize a bit, so I try to look around what has happened in the past, and I think this can be improved much more now. So for those of you maybe who don't know, there is this nice idea came from MIT 2014, I believe, see-through walls. So here you have a very basic idea. You have a transmitter, and you're transmitting RF signals in the 2.4 or 5 even gigahertz, and then you try to reconstruct the silhouette or identify kind of a heat map of the person behind the wall, right? So this is essentially very basic idea. It works. It has been demonstrated. It's just in the low frequency band. So if you apply this to the really higher band, millimeter wave, even more, I think this is extremely useful technology. Another one which I found essentially, which is for sensing and localization using RF, is this NASA technique called Finder. Actually, so what they have here, they have this kind of you can see this device here, which weighs I think around 20 kilograms, and it emits low-powered RF signals, right, through rubble, so through type of buildings, right, and it looks for reflections, and then of course it's kind of trying to infer whether there's a person there or not for further intervention. It turns out, in fact, the solution, which is very interesting, but it could be, it's still kind of it requires the human to know where to locate, to position, sorry, those devices, right? So this could be again done in a completely automated way. You can argue that maybe even the drones could be equipped with this kind of RF signals, and maybe they can collaboratively infer, right, this information, especially if they have partial information, right? So how can they cooperatively sense and infer about the kind of the vitals of some people trapped under the rubble. Yeah, and again, this will obviously, if you use swarms of drones again, reach wider areas. I think there's a lot of potential techniques here. Another one which was interesting, in fact, this is when you don't have line of sight. So in this case, you see, you need a line of sight link, right? Now, if it's obstructed, they're multipath, you are in the non-line of sight setting, where here essentially there's another technique, maybe developed by NASA. I couldn't find really the source here, but you have this large truck which is actually emitting again magneto quasi-static fields through the rubbles, right? It has a kind of a range of 70 meters or 100 meters, right? And it's again pinging back these reflections to identify the presence of potentially trapped persons under the rubble. Okay, again, why not using drone for that? Because you cannot position these trucks, for example, in mountainous areas. You cannot even reach the mountainous area. You can maybe try to set up an ad hoc network here with meshing all these vehicles, drones equipped with this type of devices. Okay. And again, these were done in the low frequency band. So you can see with me here, you have the low microwave to the higher, to go up to the terahertz band. So the terahertz band is very interesting because the wavelength is extremely small, so it gives you a much better fidelity, higher quality definition of the object you're trying to image. In fact, right, this is really imaging techniques using not cameras but RF signals, which again you can of course think about doing some multimodal sensing and fusion. RF on one hand, cameras, LiDAR. So you have a very nice setting here. Now, if you put it under drones, you have the resource constraint. How you really optimize this end-to-end, I think it's not only interesting in terms of theory, but it does have a really interesting applications. Okay. So I mean, this is just in short what I wanted to say. I mean, it is clear that communication, drones, satellites, sensing, imaging are really all key. They're instrumental in enabling a very quick deployment, because obviously here the premise is the earthquake has happened, so how do we get as fast as possible rescue teams? Where do we dispatch them? With which technology, so as to save life? And yeah, with this, thank you very much, and I wish you good continuation to the event. Thank you again.